Pa, 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 pa. In fact, I don't see my group connecting anyway, so just wait a couple of minutes. They may be late.
Yeah. Usually I wait a few minutes until 4:05, 4:07, but oh, Western is now connected. I guess they're group watching it.
Ah, okay. Should have solved the problem they had. Okay.
Hi, Francesca, where are you now, if I may ask?
It's my last opportunity to give a talk from my old house in Canada.
When do you move?
Eh?
You leave soon?
Very soon, very, very soon.
Okay. Best of luck with that.
Yeah, they are a huge, it's a huge enterprise to move a house, yes. Let me start maybe sharing my screen while we wait a few minutes to have
Yeah, you
everybody on.
can.
Could you see the change in the slide a second ago? Just to be sure that everything is working properly.
Yes, yes. Yes. Okay, I guess we can start. Let's start the recording. Good. So we are live on YouTube and we are recording. Hello, everyone. Welcome to the KISS seminar again. So today we have Francesca Vidotto. She will talk about how we can understand superpositions of space-time in the early universe and thus understand cosmological structures better.
Yes. Thank you, Ofek, and thank you, everybody from the KISS community, all the people that have been organizing these seminars in the past years. It's a pleasure to be a guest of this series. I'm going to talk about a research program that has been my focus for many years. I'm going to give a review of what has been done and some recent progress, and maybe an outlook of what I think should come next. The idea is that I'm going to talk about space-time superposition. This is one of the focus of the KISS community, describe superposition of space-times from different perspectives and using different techniques. And here I want to tell you how I have been superposing space-times, superposing geometries for the sake of describing the early universe, and then trying to connect with standard cosmology and the physics of the primordial cosmological perturbations that give rise to all the structures that we see in the world. So that's my motivation. So as I said, I'm going to provide a bit of an overview, and since the community is very diverse, I will try also to touch on some fundamental topics like what is a wave function of the universe. I will give you my take of how I think we should think about a wave function of the universe, a quantum state for the whole universe, in which sense this is something viable. And then to do so, I will work in the framework of covariant loop quantum gravity, that is generically known as Spinfoam. And this is different from what some of you may have heard, putting together cosmology and loop quantum gravity. Most of the work in the literature, very successful work in the literature, has provided many predictions. It's done with the canonical theory. So the theory that is based on the dynamics, they use the Hamiltonian constraints. So here instead I will exploit the path integral formulation, if you want, of the theory in order to define some cosmological states for the universe. And careful, these states will be fully Lorentzian. This is a difference with respect to other approaches to the wave function of the universe. And then, of course, the goal of all this program is try to describe the quantum fluctuations that pertains to these states. Of course, this is a very difficult task, so it requires to use numerical evaluations for the different quantities that characterize those states. And then I can connect also what we are doing here with a more traditional approach to quantum cosmology, to loop quantum cosmology, in which instead of an initial singularity, you have a bounce. So the universe goes through a contraction that achieves a maximal energy density state, and then it starts expanding again. So I will connect to that picture in the semi-classical limit of what I am describing. Okay, so before starting, let me just tell you a bit about the fact that this is a very large research program that started many years ago. So here you see just some of the papers that have been developed in this context, but I will focus on those oops, something happened, to those more recent results. In which we have been able to tackle the question, as I said, of cosmological perturbations from a new perspective using numerics. And something I want to mention here is that, of course, there is much more to be done, and I wanted to put here also a couple of recent works by Eugenio Bianchi and Rinco Ramirez and Wolfgang Wieland, even though those works were not originally developed specifically for cosmology, but I think they goes into this direction of trying to use the spinfoam formalism to do phenomenology, to give predictions for loop quantum gravity. And my hope is that we may be able to use those recent works also to talk about primordial gravitational waves with spinfoam cosmology. So what is quantum cosmology, to start with? Well, quantum cosmology traditionally is the idea of restricting ourselves to few degrees of freedom, the cosmological ones, namely just the scale factor or few anisotropic degrees of freedom. And then once you restrict yourself from the infinite degrees of freedom of the full theory of the full general relativity to these few variables, it's easier just to quantize those variables, and hence you get to quantum cosmology. Now, of course, this rely on not just on an idealization that the universe is homogeneous and isotropic, but also it relies, I would say, rather on approximations. So what about when you are out of those approximations? So a way to arrive to quantum cosmology, an alternative way, that is now available to us, is to start from general relativity, go to the quantum theory, and then from that try to derive a cosmological sector that, again, doesn't have to be an exactly homogeneous and isotropic one in the sense of imposing strongly some mathematical symmetries, but rather trying to define homogeneity and isotropy with what remains of them in the cosmology, in the quantum theory. So the advantage of this is that we can start from the full theory and exploit all its potential to try to describe the early universe. So even when we are in the deep quantum regime that otherwise would be not accessible because it would be out from the approximation that they used in the standard approaches to quantum cosmology. So just a short recap for everybody, especially for those who work, who doesn't work in cosmology, who are less familiar with it. Just to flash where we are. Usually in cosmology we use the standard model of cosmology, in which there is a Big Bang. The universe started in a hot and dense regime in which quantum fluctuations are produced. For these quantum fluctuations, we can then we can evolve those fluctuations so that we recover the large scale structures that we see in the universe. And usually this framework works with an extra field that is usually put by hand, that provides an inflationary phase. And inflation in cosmology, what it really does, the question that really address is how to obtain later a almost scale invariant power spectrum. But of course, this requires also ad hoc initial condition, in particular, the choice of a vacuum state. Usually, people take a Bunch-Davis vacuum. But again, this is something you do ad hoc to fit your general picture of the universe. So in loop quantum cosmology, first of all, we don't have singularities. This has been explored a lot in the canonical theory, but there is also a very general way to see how it's impossible to produce strong singularities with the covariant theory. So generically, one expected to have a bounce, so a period of contraction followed by a period of expansion of the universe. And there are different ways in which one can think of this. In loop quantum cosmology, in the canonical theory, we can follow the trajectories of the geometry through the bounce. When we move towards the covariant theory, we would rather think of this as a tunneling process in which we have a geometry that tunnels from being, as I said, with an extrinsic curvature corresponds to a contraction, to a geometry with an extrinsic curvature that is like flipped and corresponds to an expansion. So one good news about loop quantum cosmology is that inflation is generic in the theory, but something that I like even more is that we can also develop alternatives to inflation, for instance, using the formalism of the so-called matter bounce, of ekpyrosis, and so on. In every case, the question remains, that is, what is the vacuum state with which we want to work? Loop quantum cosmology really doesn't address this question in the sense that if we are at the bounce, we can describe the universe in a very rough way, but we don't have access to a description of all the quantum fluctuations happening at the bounce. So what I would like to do using the covariant theory is to define a vacuum state that makes the job, that it's in all its validity, it's in a regime in which it's fully valid at the bounce. And so I can compute from scratch the characteristics of this state and eventually connect this with the perturbations that leads to structure formation. Okay. Here, I wanted to add a bit of philosophy and connect with some of the work in Quantum Foundation that is also done in our community, because in order to do quantum cosmology, of course, we need to work properly with our quantum theory. And one of the questions is, what does it mean to make a measurement of the universe? And in particular, often you may find in the literature some confusion. For instance, what does it mean to make a measurement when we are inside the system, the universe? So we are inside in the system that we want to measure. Is it something viable? Does it make any sense? So let me break this for you in this way. So, of course, when we do a measurement, we make a partition. This is something that is always required when we do when we use the quantum theory. So the question here is, what is the partition that we use in cosmology? The best way to think of cosmology is in terms of an expansion in modes. So the kind of partition you work with in cosmology, they are not like, oh, we are here and there is a system that I'm measuring there, okay? It's more like the fact that we have an expansion in modes. That means that we start with a description that corresponds to the largest scale of the universe, namely what is described by the scale factor. And then we add modes one by one. So these modes will describe scales that are smaller and smaller, just like 1/2 of the universe, 1/3 of the universe, 1/4 of the universe, and so on. And in this way, we recover a description that takes into account smaller and smaller degrees of freedom, till the point in which we recover the full theory, the full general relativity. So when we said before, cosmology is a sector of general relativity in which we use just a few degrees of freedom, well, these degrees of freedom are the first ones of this expansion, and then we disregard the others. So where are we in these degrees of freedom? Well, we are at the very last, we are within the very last terms of this expansion. So we are very small degrees of freedom that are not part of the large one that we are describing. So we make measurements from our perspective. We make measurements of the large degrees of freedom of the universe, and careful here because of course we make measurements here on Earth. So we use our instruments. I don't know. We measure the CMB, and the question is, where is the classical to quantum transition? Where is that I go from me as an observer, observing something that is a quantum universe? Well, here I can exploit the Heisenberg cut, the fact that I can move my Heisenberg cut, so I can move it away from me, here really in a spatial term. But remember, in cosmology, the more you are far away, the more also you go back in time. So you make your measurements here, and then you move your Heisenberg cut till the moment in which you reach the surface, let's say, in which the universe was indeed in a quantum regime. So that's the way to think of doing quantum cosmology from the perspective of quantum foundation. And here I want to show you how the formalism of loop quantum gravity somehow naturally allows us to talk about cosmology in the following way. So in loop quantum gravity, we describe spacetime, generic spacetime, using a truncation of the degrees of freedom of the theory. Namely, we make the composition of the spacetime that we wanted to describe, so that we describe different regions, and we label each region, putting a node there, and then we put a link to say that between one node and the other node, like labeling one region and another region, and we tell that this regions are in interactions. And by the way, interactions in general in the quantum theories, like when we use cross sections, we always use area to tell the strength of interactions. So indeed, this link corresponds to areas. So for each region, I have a certain volume, and I have some areas that define the boundaries of this region. Well, okay, I don't go into the details of the fact that we use group variables. The theory is fully developed as a gauge theory with a gauge group that is the Lorentz group, but here we restrict just to the rotation group. And so the point is that we have these objects that are nothing but the spin networks that were originally proposed by Penrose in the 70s. And as you can see, so this way of describing space-time can naturally embody this idea that I can have a decomposition in only a few degrees of freedom, So I can make a decomposition of my space-time in only a few cells and restrict to few degrees of freedom in this way. And then, of course, the way in which I recover the infinity degrees of freedoms of the full theory is by refining my graph, making my graph more and more complicated. Adding nodes, adding links, and so on. But the main point here is that you use the kind of state that is more appropriated for the kind of physical situations you want to describe. So depending on the kind of geometry you want to encode in these graphs, your graph can be more or less complicated, so it can allocate more or less degrees of freedom. And for cosmology, we just need a very simple graph. It could be just two nodes. So if you have two nodes, two volumes in interaction one another, you have already more degrees of freedom available than in standard cosmology, in which you have only one, the scale factor. So two nodes in interaction, two regions in interaction here can already encode some inhomogeneities or anisotropies. And so if you have even more nodes, you can really have a very rich description of your space-time, a description in which you have a finite number of degrees of freedom that is able to capture the physical problem that you want to address. So again,
Francesca?
yes.
There was a question in the chat. Do you want to take questions now or only?
Yeah, sure. Sure. Can you read it to me? Because I am in full screen mode.
So Arthur is asking, was it explained what these important degrees of freedom for quantum cosmologies are more concretely? I somehow missed this.
So, sorry, I missed the beginning of the question. What are the degrees of freedom that are important for cosmology? Well,
For cosmology, yeah.
Yeah, so in cosmology, the physical variable that you consider is just the scale factor that corresponds to the size of the universe. Of course, you can make your description a bit richer, so you can have a few more degrees of freedom adding inhomogeneities and anisotropies. So here we are talking about 1 degree of freedom, or possibly, I don't know, a few more. So what I want to do is to have a graph that encodes the same number of degrees of freedom. In terms of quantities, physical quantities that are relevant, I wanted to have my description in terms of volumes, for instance, area and volumes. Again, you can think about cosmology as a description of how the total volume of the universe changes with time, and how as this volume change, the perturbations, the small anisotropies and inhomogeneities on the three spheres with which we model the universe, how these perturbations evolve as we change the scale factor, as we change the size of the universe. So here we wanted to have something like this. We wanted to have a proxy for the total size of the universe, say the volume, and we wanted to see how some perturbations, some fluctuations changes as we change the volume. I see somebody nodding, so I guess this should be reasonable.
That helped. Thank you.
Yeah, okay. I wanted to put a caveat at this point, that is the fact that when we use these graphs for describing the geometry, we are doing an approximation, right? We are truncating the number of degrees of freedom of the full theory. And of course, every time you introduce something like this, a graph or a lattice and so on, you do a form of discretization. But careful, this is not the discreteness that is characteristic of loop quantum gravity. As I said, this is just an approximation that we adapt depending on the physical situations that we want to describe. A different thing is the fact that in loop quantum gravity, we have observables that are geometric observables. Again, like the volume could be the volume of a small region of Planck sites or the volume of the universe. And this quantity, we studied the spectrum of this quantity, and we see that it has a discrete spectrum. And so we can do this for different geometrical quantities. What does it mean, geometrical quantity? It means like area, it means like angles, and so on. When we do cosmology, of course, there is a non-trivial interplay between these two different senses in which we have discreteness. So, of course, when we talk about singularity resolution, when we talk about the bounds, what is important is the full quantum discreteness of, if you want, of a quanta of space-time. And this is different from the truncation. The truncation has to do, again, with the cosmological approximation, if you want. So what we do when we do quantum gravity, and especially when so we wanted to do a measurement for a region of space-time. One important characteristic of the way in which we proceed in loop quantum gravity in general is the fact that we privilege to work with finite region of space-time. So here what I am depicting, it's just a cartoonish version of a four-dimensional Lorentzian space-time region. So we don't make measurements at infinity. We make measurements on a finite region. So again, careful, you have to make a partition. You have to decide what is the relevant region that you want to describe. And then the states of the theory live on the boundary of this region. And if you want, what the dynamics, the covariant dynamics does for you is to reconstruct what is in the bulk of this region. So namely, so if you take, say, just to fix the ideas, take the bottom part of this space-time region. Let's call it, my in state. So then I want to make a transition to the upper part, my out state. And the magic of what we are doing is that this process that I am describing, transitioning from one part of the boundary to the other part of the boundary, with the partition that I have chosen between in and out, corresponds both to a process, a quantum transition, but also is what defines space-time itself. It builds up the fabric of the four-dimensional Lorentzian space-time itself. So this is magical, and at the same time, that's one of the hardest part to digest. Okay, so careful now. What we wanted to do is to describe transition amplitudes. These transition amplitudes are like the probability to go from a given state of the geometry to another one. But we will see that we can play with this, and we can play with partitions. So just a sketch of what we want to do. We want to compute, as I said, the transition amplitudes, so probabilities to go from one state to another state. So what covariant loop quantum gravity does for you is to make sense to the gravitational path integral that was originally written by people like Hawking and Halliwell, in which you have this sum over possible geometries that interpolates between the geometry and the boundary of a region. This is what is expressed in this formula here at the top of the slide. So, and loop quantum gravity, of course, is a tentative theory of quantum gravity, but it has a number of nice properties. So it has the superposition principle. There is a vertex expansion, very much as you have seen if you have done some quantum field theory with the Feynman diagrams. So I recover the full amplitude, adding piece by piece, and each piece can be written in terms of some, not a Feynman diagram, but a spinfoam, that is the gravitational analog to a Feynman diagram. And then, as I said, there is Lorentz covariance. The theory is, in a genuine way, a gauge theory based on the Lorentz group, and this transition exploit the properties of the representations of the Lorentz group, in particular the unitary irreducible representation of the Lorentz group. So you can extract from those properties the way in which the dynamics is defined. Further properties, of course, the result is that you have transition amplitudes that are finite in the ultraviolet, finite in the infrared, if you add a cosmological constant. And there is a theorem that tells you that you can recover classical general relativity as a limit of this theory. Okay, so what I don't know if you can see this little animation. That's good. Okay, this is just to give you a pictorial idea of what's going on. So we can have a devolution of some quanta of space-time. You have a vertex. The vertex creates new quanta. So your new state is given by, say, 3 quanta of space-time, and of course the initial quanta and the final quanta, they are all represented by these graph states, the spin network. So here I computed the probability to go from one to the other. So here I wanted just to sketch an example of a research work that is principally the work by Dong-Xue Hu, and also in collaboration with Muxi Nan, with Hongguang Liu, with Kong Zhang. This is an example, sorry, I mean, you see this is a very messy graph. It's messy because it's really a complicated calculations. So this is what I told you before. It's the analog of Feynman diagram, but in the gravitational sector. And this is the kind of structure we use to compute transition amplitudes. Transition amplitudes, in this case, from a hypercube that represents a contracting geometry to an hypercube that represents an expanding geometry. So we can really model in this way a bounce, but careful, as a transition amplitude, all you get is, given a state, that's the probability to obtain the other state. You don't get trajectories. That is what you get in the usual description of a bounce. So I don't get the full description of the geometry contracting and expanding. If I wanted to do so, I have to study the semi-classical limit of this theory. And this is something that can be done. So you can recover the usual sense in which the bounce appears in loop quantum cosmology, having this process, studying this process in the semi-classical limit, and studying the new terms that appears as a correction to the classical dynamics. And these terms basically have the shape of higher derivative terms. So this is something that can be done. But let me tell you a peculiarity of what we are doing, because this is important for the study of perturbations and so on. So here, let me start from just Hamilton-Jacobi, standard dynamics. standard classical dynamics, and I do the dynamics of the universe just for the scale factor with a cosmological constant. So my Hamilton-Jacobi equation gives this. So you have a difference with the scale factor, the derivative respect to cosmic time of the scale factor square minus the cosmological constant divided by 3 to the volume of my universe, okay? So why I'm doing this? Because I wanted to show you the following thing, that, as I said, when I compute this, and everything is just described by a difference between the initial and the final volume of the universe, okay? So when I go to the quantum theory, this difference between two volumes corresponds to a factorization between the amplitudes for my state in the initial volume and the amplitude for my state in the final volume. So now in the quantum theory, so this is true only as a first term in an expansion in H bar. There are other terms, but these two factors embodied the terms that are the heaviest one, the one that determines the full process. Okay, so when I do the same kind of calculation in loop quantum gravity, what I see is that there is also this factorization. So what I have is that at the zero order, I start with a given geometry, a given graph that goes into another state. Sorry, at the zero order, nothing changes. So if I wanted to go to the first order, I can imagine the process as a factorization, but the factorization means that I can represent this process as the universe, my state, going into nothing and then into something again, okay? And then, of course, again, this is just the first term in an expansion in which here I have a single vertex. That's why I have the factorization. In general, the full amplitude is given by summing over many vertices. But the idea, if everything goes right in the theory, is that by studying just these objects, the product of one state to appear from nothing and the process of one state of going into nothing. So if I study just these things, I can get basically the dynamics of the theory, the leading dynamics of the theory. And this is exactly what traditionally defines an ortholocking state, that is like a transition from nothing into something. And so we can really think of an ortholocking state in this way, as Hartle and Dawkins told us, as a transition from nothing into something, as a transition from going in from an empty state into some state of the geometry. But a better way, in my opinion, to think of ortholocking states is, as I said, as part of, as an ingredient for general transition amplitudes between one state and another one. But the good thing is that now I can just study this object, the ortholocking state for loop quantum gravity. Careful again, here it would be a fully Lorentzian four-dimensional state. We don't have to add Euclidean phases to do so, to compute this object. And this is the state for which we want to study the properties, the fluctuations. The idea is that I can study this object like a transition from nothing into one state. The magic of this is that now the resulting state is not just a given fixed geometry, but it's a superposition of different geometries. So when I study when I characterize my state as being a cosmological state, so being labeled by some quantum labels that are that corresponds to a given size of the universe, a given volume, let's say. I do have a state that is basically picked on a given size, a given value for the universe, but I do have all the fluctuations that comes from the fact of having a superpositions of geometry. And this is the trick, this is the main point that allows me to study fluctuations and correlations and entanglement entropy and so on. Okay, so then the question is how complicated should be my graph to study properly correlations and entanglement entropy? Well, the problem is the more informations we can add, the better for us. But unfortunately, we have to face reality, namely the fact that the larger the graph we try to handle, the more the calculations get complicated. So we have to find a good compromise. And as I said, of course, if we want to do cosmology, the graph could be kind of simple. So for instance, it could be like the one in black there with 5 nodes. So this means that I am taking the composition of my space-time. Think about a 3-sphere, like Einstein liked. I just think about the universe as a 3-sphere. And then I have 5 regions. I divide it in 5 regions, 5 cells. And I study how the volume of each cell correlates to the other. The problem is that when you do such a thing, each region is in interaction with all the others. So more concretely, if you think in terms of each node is dual here to a tetrahedron. So we have 4 faces, and these 4 faces, each of them is represent the interaction with one other node, with one other tetrahedron. So of course this is very correlated because everything is interacting with everything else. So the goal is to go to something more complicated, like the graph that you see below, that is the next regular triangulation of a 3-sphere with 16 nodes. And in this way, some nodes are interacting with the others, with an adjacent one, and some nodes are not interacting with all the others. So in this way, you can put the nodes in different, so you can pair the nodes in different ways, putting them in different categories, those that are in direct interactions, those that need to pass through another node to interact, those who needs 2 other nodes to interact, and so on, so that you can have a proxy for the distance between the node in this way, in this combinatorial way. But let me tell you what we have done at this point. This is the main message. How do we compute correlations from scratch in this context? So we have the simplest thing that we were able to do was, as I said, to start with a graph with 5 nodes, namely a regular triangulation of the 3-sphere that we call the pentachords, if you want. And so in this picture, what you have is that you can, so the way in which we talk about cosmology here is to label this geometry with a single quantum number, a spin, that is all the same for in each different sites. So in this sense, the overall geometry is characterized by just one number, if you can think about this, like the overall scale factor, and so this is a way in which we represent the homogeneities of our geometry. But again, as I said, so you can think about each of these sites as a volume characterized by some areas. We fix the areas and we let the volumes and the angles. So if you have like this chunk of space-time, you fix the areas that characterize the boundary of this region, and then you let the volumes and the angles between the different faces to fluctuate. So then, so you can describe correlations between different regions in terms of angles and volumes. So this is what we do. As I said, area, volumes, and angles are the characteristic geometrical quantities that for which we can write operators in the theory. And we can study the spread of these operators. But in particular, what I wanted to do is to study correlations. So I can pick up one of these observable in one site of this decomposition of my geometry. I take the same observable in another site, and then I study the correlations between them in this way. And of course, I can also write the corresponding entanglement entropy. So I have a partition with two regions. I computed the entanglement entropy between these two regions, and this will be what gives me an upper bound to my correlations. So just to give you an idea, this is what we have been studying in the past. So with the kind of numerical computations that we have done, we have been able that we were studying a genuine geometry, not a degenerate one, a geometry that was indeed corresponding classically to a tree-sphere. And then we can study the fluctuations of the observables in this geometry. We can observe the presence of large correlations. But as I said before, we have to be careful studying these correlations. We should take this correlation with a grain of salt, because these were studied for the case in which all the regions were maximally connected. So we tried to make a graph refinement first to study things in a more complicated setting. The problem is that if you just make like a graph refinement like this, so you start with your 5 sites and you split each of them in 4. The problem is that when you do a refinement like this, you still keep the memory of the fact that the initial regions, the final regions were initially connected. So again, we find strong correlations there, but we have doubts about how genuine they are. So here, so one can study, as I said, entanglement entropy also in this case. Just to give you a sketch of what we do, you can pick up one region, choose your partition, choose one volume, one cell, one tetrahedra if you want, one volume, and see the entanglement entropy with all the rest. You can also, and then when we do the refinement, we can do this further. And we can choose different partitions in this kind of geometry. But the interesting thing comes, as I said, we can study correlations in this case, and then the entanglement entropy in these cases. I wanted to make just a short comment at this point, because what we have seen is that we obtain results that are very similar to those for Bell network states. So this is an interesting connection that needs to be developed, even though this connection comes when instead of doing the computation for the full theory, we compute things in the simplified framework of a BF topological theory that is easier to handle, is more accessible. So same thing when we try to address the real thing, that is a partition of my geometry into 16 sites. So why 16? Because we want regular decomposition of the tree-sphere, because the regularity, namely the fact that each node has the same degree, and the angles between the different nodes, so all the angles in the geometry can be approximately the same. So we have a residual notion of homogeneity and isotropy here. So this is after the 5 nodes, 5 cells case. This is the next regular triangulation of a tree-sphere. It has 16 sites. As I said before, it has the advantages that some nodes are directly connected and some of them are not. So we have a proxy also for distances, and we can study correlations between nodes in these different categories, whether they are adjacent or not adjacent. So this is very promising, except that so far we have been able to handle this only in the simplified BF case. Again, this is the case in which we find back the results similar of what we have with Bell network states. And here what you see is that we have studied correlations. In fact, we have some correlations and some anti-correlation. But still, I think this is already very interesting and very promising, because this is a way to start with a state of the geometry in loop quantum gravity. So here we are not picking up the state, let's say, by hand. We let the dynamics pick up the favorite superposition of generic spin network states. So then we can study correlations. And again, we have correlations that are smaller, but they are present. That means that, in particular, also when we study, for instance, the evolution of perturbations in cosmology, we can start with a state in which correlations are already present and they don't need to be developed later, like you have with the Bunch-Davis vacuum. So there is even the possibility that we can do without inflation. So this could be a further motivation to look at something beyond inflation, because we can handle correlations here from the beginning, being present in the quantum state as defined by the full theory of quantum gravity. And of course, this is commented that for the moment, the results is only for the simplified topological theory and not the full amplitudes. So the goal now is to connect in the semi-classical regime with what we do in quantum field theory and quantum field theory in cosmology. The problem is that in most of the cases, people in cosmology studies correlations and entanglement entropy only by taking one region and looking at the correlation with all the rest, or taking one region and studying the entanglement entropy with all the rest. And things have changed for the first time with the work by Ivan Agullo and collaborators, in which they started to do something that is more similar to what we do, namely like putting fluctuations, putting the fluctuations of the geometry on a lattice. So then I can compare different lattice sites. That is exactly what we do in this quantum gravity model. So to summarize, we have been studying primordial quantum fluctuations from scratch, computationally, in loop quantum gravity. This is now accessible to us, it's possible. We have been exploiting the idea that we can study just these spinfoam Hartle-Locking states. We have been progressing, trying to study geometries in which we include more and more degrees of freedom, from the case with just 5 cells, 5 sites in my spacetime, as the composition of my spacetime, and then moving towards this 16-cell model that is more complicated, has been addressed just in a simplified version, the topological one, but the challenge is now to push the numerics to possibly in the future address, fully develop this model for the full Lorentzian loop quantum gravity transition amplitudes. And the results that we have obtained so far seems to indicate that, so indeed you start with this generic combinatorial graph states, and we have indications that what we have is indeed the geometry of a 3-sphere that is encoded in these states. There are fluctuations of the geometry, and there are correlations. The question is how strong are these correlations? Could they even supersede the necessity for inflation? That's an open question. But here we have a model in which instead of starting from cosmology and try to adapt things to our expectations, we can start with the theory of quantum gravity, fundamental theory of quantum gravity, studying superpositions of geometries, and study the properties of this superposition and geometries, and try to offer to cosmology some fixed points with which the cosmological models needs to be constructed. So coming back to the beginning, I have been speaking about a possible way to see the wave function of the universe. I gave you some ideas about why I think it's viable to even think about doing quantum cosmology, so writing a quantum state for the whole universe. This is from the perspective of foundations of physics viable. It makes sense because of the approximations that we do in cosmology, and it makes sense with respect to how we understand measurements in the quantum theory. Then I gave you some ideas about how using this formalism, covariant loop quantum gravity, dubbed also spinfoam, I can write a Hartle-Locking state for my universe. Now it's a state that is a spinfoam state. So again, superpositions of geometries, but superpositions that are chosen by the dynamics. So in other words, the transition amplitudes act like projectors on the physical states of the theory. So they pick up those particular superpositions that correspond to physical states. And so those objects are, as I said, fully Lorentzian. We have seen that they fully represent a geometry that can be interpreted as cosmological 3-sphere for the universe. I haven't been going too much into the semi-classical techniques that connects these objects, these quantum objects, to the classical framework, namely recovering general relativity, but so this kind of passage is necessary when we want to give a description in terms of a bounce, so following trajectories for my geometries, for my quantum states, so that I can really see all the stages of collapse and expansion of the universe. So techniques are available and they are under development. I show you a recent work in which we have started to do this with my Chinese collaborators. And all these results relies on the fact that in the past 10 years there has been a momentum development for numerical techniques in loop quantum gravity. And there is always a back and forward between numerical and analytical techniques. Sometimes the numerics bring us forward, then we hit a wall, we have to do more analytical studies. So it's like understanding what the numerics are telling us and massaging our equations so that we can put them in a form so that we can evaluate them better with the numerical results. The magician that does this, well, on one hand, the analytical massage is Simone Speziale, and the numerics expert for this is Pietro Donat, both in Marseille. So if you're curious about this, ask them. And I want to close mentioning again that I'm very, very excited by the work by Eugenio Bianchi and collaborators, the work by Wolfgang Wieland. All these works hint to the possibility to study phenomenological signatures of loop quantum gravity in gravitational waves. This should be possible for gravitational waves coming from, for instance, black holes that are merging. But to me, what is really interesting and what's the next thing that I want to study is to use these ideas to address the question of primordial gravitational waves, because experiments are coming in the future. Well, okay, you know, this is astrophysics, astronomy, so maybe we'll have to wait for some 10, 20 years, 30 years, I don't know. But in the same way in which Kip Thorne was lucky and pushed for 50 years to have gravitational waves detectors, and he was rewarded with a Nobel Prize. Well, I think that we can wait for LISA and with the other great, or the Einstein telescope, all the other, or even, let me mention, even detectors of gravitational waves using Bose-Einstein condensates, for instance. So I think there is a richness of experiments with gravitational waves in the future, and I would like to bet on them and work to make my predictions from loop quantum gravity. So that's all I wanted to say, and thank you so much for your attention. Thank you for those that are making the clapping. I can see you.
I'm looking how to make it. Ah. No, it should recognize my hand gesture, but I don't know. I will just do this. So thank you, Francesca, for a very interesting talk. It was really interesting. I would like to shamelessly abuse my role as a host and ask the first question. It is about the Heisenberg cut.
Yep.
So you say that you split the universe to the time when it was quantum, and after this time where we assume it is classical. Now, if we assume that the universe as a whole is quantum, shouldn't also the classical part, or like the later part, still be quantum because it is isolated up to the interaction with the quantum part?
No, I think, yeah, I don't know. I hope I'm not missing part of your question. But of course, no system is never in complete isolation. So when we make partitions, we are always cutting in a rough way. But so as I say, the partition I'm making here is a partition between different modes and that are clearly separated. Okay, so we ourselves are these very short modes, and the universe is the largest, corresponds to the largest modes. So, and in the between, there is a lot. So in this sense, we are clearly separated, let me say. Of course, spatially, I mean, we have to be careful because in quantum mechanics, not all partitions are in space. You can have a different kind of partitions for your Hilbert space, but also in the case of the Heisenberg, the cosmological Heisenberg cut, there is really also a spatial and temporal partition, in the sense that we make measurements here and now around us, okay? And then we move the Heisenberg cut more and more far away from us, okay? So, and then the question is, how far can we move the cut? Well, a lot, till the point in which we reach the regime in which the universe was a quantum one. So careful, because as I said, in cosmology, you move far away from yourself, but you also move past in time. So there is this double separation in space and time that separates you, the observer, you, the one making the measurements, from your observed system.
Okay.
So, but your question was about how isolated we are. Is it?
So, sort of, because if we assume that the universe as a whole is quantum, and there is no real Heisenberg cut, so the Heisenberg cut that we introduce here, it seems like it would make the results be a post-selection of what happened in the early universe based on what results we see in the later time. Because if it's always quantum, then the part where it is classical, well, it's only classical because if we observe it, we
look, but can't you always say that? I mean, we ourselves, we are always also quantum. It's just, again, a matter of approximations that, well, yeah, I mean, myself, I am quantum. Everything is quantum in the real world. It's just that I am more classical than the thing that I am measuring.
Yeah. Okay, so I guess so we are sort of post-selecting what happened in the quantum universe based on what we see today. Yeah, we don't have any other way to do it. Okay, thank you. So, Eugenio, please.
Hi, Francesca, hi, everybody. Francesca, can you say more about initial conditions? You had this nice description of like the standard story with perturbations and Davis vacuum, and now the wave function of the universe in spinforms. What are we learning about initial conditions in spinforms?
Well, for the moment, as I said, we have to take with a grain of salt all we are learning because these are very rough model. But let me answer, giving a bit the standard picture in cosmology. Thank you, Eugenio, for giving me the opportunity to do so. So the standard story is that we start with a Bunch-Davis vacuum. The Bunch-Davis vacuum in cosmology is a kind of vacuum that is constructed in order to fit with the adiabatic expansion of the universe. One thing that we already learned with loop quantum cosmology, not even with Spinfoam, is the fact that in the moment in which you have a bounce, your initial state cannot be a Bunch-Davis one, because the bounce excites the geometry. And the Bunch-Davis instead is not excited, so it should be something else. There should be something else there, some excited state. Again, we want a theory that is able to capture these excitations. So here I turn to covariant loop quantum gravity and to Spinfoam, and I want to study a state as selected from the dynamics. And my expectation, my hope is to see that the excitation that loop quantum cosmology were suggested are indeed there. And the fact that we do see fluctuations and we do see correlations, for at least for the kind of model as rich as we could handle. So we do see these correlations, we see these fluctuations. And then we can reverse the question. So Bunch-Davies was put there to fit with inflation. But if instead we start with a state that is different from the Bunch-Davies one, do we still need inflation? Or maybe we need an inflation that is shorter, we need something else? Or can we do even without? Does this suggest that models without inflations, like the ekpyrotic one, are viable? So these are the questions that are open. And yeah, I mean, the presence of these strong fluctuations and strong correlations seems to indicate that this is a good direction to follow. But again, before making any strong claims, we need really to be able to solve the full system with the full loop quantum gravity dynamics rather than just a topological model as we have right now. Even though I know, Eugenio, that since you're working with the Bell network states, maybe there are other ways to see that these states are viable one for cosmology. So then maybe there could be a feedback from cosmology through this other class of states, making us confident that what we are seeing is maybe something that we have to trust more because it fits well with the picture we have of the universe.
Thank you.
Thank you, Francesca. Let's take a question from the chat. Haris is asking, in what sense exactly can this formalism potentially replace inflation?
I don't know, in the sense that, let me say this again. The thing that inflation does for us is to provide a scale invariant power spectrum. So it tells, inflation provides a mechanism to allocate in a pretty equal amount of energy in each beam for different frequencies, different wavelengths that we see in the power spectrum, okay? So in cosmology, in general, we use inflation to obtain this result. But in cosmology already there are other models that can do the same job. This is well known. For instance, if we have a matter bounce, namely a contracting phase dominated by some matter, that could be, for instance, some dark matter like black hole remnants, primordial black holes, and so on. So we do have automatically such a scale invariant power spectrum. And then with the bounce again, you have the presence of this excited states. So if you study the geometry at the bounce, you do have excitations. You do have fluctuations, correlations, and so on that are already present there. So in this formalism, we want to support this kind of framework, seeing the correlations and seeing the fluctuations as property, general property of the quantum state of the geometry in that particular regime. So if you can get this kind of support, again, you are able somehow to predict the initial conditions of the universe rather than having to infer it in a way that fits well with your own model. And again, you may not require, and this may challenge, as I say, the inflationary scenario. Again, it's not like a complete cut in the sense that we do this calculation and then we eliminate inflation. It's more like making the necessity of inflation less and less strong, possibly.
Okay. Do we have a comment from Javis? Ah, okay. Good. Let's now get the question from Deepak and then Arthur.
Yeah. Hello, Deepak.
Hi, Francesca. So thanks for that really nice talk. And I just want to say that, personally, I haven't kept up with many of the developments in spinforms over the past few years. So this is one of the first talks that I've seen. And seeing this makes me feel very positive about the future and the present status of our field. Because until a few years ago, maybe 10 years ago, it was a theory. It was a very nice theory, but it was just a theory. And it was hard for people to really, say that, okay, this describes our universe. I mean, apart from all of us who believe in it. But now seeing the level of detail that you're able to access in your numerics, I have this feeling that it's going to become more and more difficult for, people outside the community to ignore it, to say that it's.
I wish evidence and calculations were enough to convince people, but that's not how
of course
psychology works. But thank you so much, Deepak.
No, of course they are. Of course, that is the only thing that does convince people, right? And along that line, I just want to stress that another way that we can really make an effort to connect with what others in the field, broader field of quantum gravity are doing, is to use these methods, for example, to look at wormhole contributions. That's one of the things that's being looked at by people like Netta, Engelhardt, and all. And I'm sure that Eugenio and maybe others already know about that. And if you could find a way to do some computations in the spinform picture with that, and connect that to that wormhole contribution picture and factorization of the partition function and all, that would be really, really.
Deepak, let me make a comment on this point, because I think one of the strengths of this research program is that we don't add extra exotic ingredients. And the connection here is really with, for instance, the quantum information community, in the sense that we are both talking about superpositions of space-time in a very concrete way. One possible connection that I see is also the fact that these spinform calculations can be done also using quantum computers with some kind of analog systems for quantum geometry. So this is a direction very concrete, attached to experiments that I think is fruitful, and this community is really bringing forward this kind of positive connection. I think that wormholes are fancy, are very good to make in movies, but I don't want to add my physics, I understand that they can be a very, so of course, I don't know if when people talk about this, my impression is that they are computational techniques to achieve some results. In this sense, it's very interesting. And for instance, mathematical tricks like the replica trick, so-called replica trick, is something that we study also in my group. Eugenia Franceschi is an expert of this. But as long as they stay a calculational trick, here, frankly, I don't see the necessity. We can talk about entanglement entropy. Also, I think that something that this community is developing is a wonderful framework for describing thermodynamics in a covariant way, so using, of course, reference frames and quantum reference frames, but without having to rely on a background fixed structure. So I think that this community really have the strength to do some solid work and bring forward some results that are gonna stay beyond movies, fashionable movie physics, you know.
That's up to you. I mean, but your work is really, really, what do you call it, promising. So I like it. Yeah.
Thank you so much, Deepak.
Okay, Arthur, please.
Thank you for your talk. I had a few questions, but I think they're maybe a little bit on the basic side. So just to get some understanding, one of the things that you looked at was like how these states evolve under some sort of a process. And for example, you went from nothing to something. And I just don't, how do you understand that from a quantum information theoretic perspective? Do you start with a Hilbert space, the Hilbert space changes? Are you applying a unitary operator? Is it a quantum channel? What is the actual evolution? Is it indivisible? So maybe you can shed some light on this, because I think I missed.
Here I don't want my Hilbert space. So once I fix my graph, so the general Hilbert space of the theory is defined as a graph space very much of the like that you have in lattice QCD. So in lattice gauge theory in general. So it's a Hilbert space defined with a limit for infinite lattice spaces, okay? But this is the general mathematical definition of the theory. And in practice, what we do is always to compute things with a finite number of degrees of freedom. So this is equivalent of what you have in quantum field theory, for instance, when you define your Fock space for particles, right? So you have the Fock space, whose mathematical definition is for an infinite number of particles. But then you work with a truncation, also a truncation of your Hilbert space, in which you take a finite number of particles, and you go from, say, 1 particle to 3 particles, or 2 particles with some spin to 2 other particles with different spin. So in our case, for instance, if I want to, especially if I wanted to preserve the geometrical interpretation of my states, so say I start with a graph with 5 nodes, and I want my evolution to give in a new state with 5 nodes. So in this sense, before I was saying the number of nodes are a truncation that capture the relevant degrees of freedom of the theory. So if I have to think in a Hamiltonian way, in the usual Hamiltonian evolution way, I start with a certain geometry that is homogeneous and isotropic with, say, I don't know, 3 degrees of freedom of anisotropies, just imagining. I wanted to have my new state that is also homogeneous and isotropic with 3 degrees of freedom of anisotropies. So I want the dynamics to preserve this, the approximation. But here is just a matter of controlling the kind of approximations that you're doing. It's not about a very deep statement about the world. It's about you operationally as a physicist. You make a measurement and you want to stay with the approximation you have chosen. So in this sense, you truncate your Hilbert space to a certain number of sites of tensorial products, and you go into another one. And then, so that's for, it's operationally for your Hilbert space. I don't know if does it
Okay.
answer already your question, or maybe there was something more I can add to.
Yeah, so I think the point is that the nothingness is actually a vector in your Hilbert space,
Oh, yeah,
and then
Sure.
what you do is you're
That's a
applying a
point.
unitary
That's a
operator.
recent point.
Oh yes, Carlo. Yeah. So, what Carlo is hinting, and then I let Carlo speak about this, is that
Yeah, I just
Carlo said it.
go ahead. No, everything you said is correct, of course, but our question was more anything more simple, and from your perspective, I think an answer could be this one. What Francesca calls nothing, it's just one particular state in the Hilbert space.
Yes.
So what she's doing is just the transition between that state to another state. It's like a little bit like the vacuum in quantum field theory, right? It's not nothing, it's just one particular state. And there, the question about why the state live at the boundary, if you think the logic here is thinking in standard quantum mechanics, you can think in terms of a sequence of measurement, right, or preparation measurement. So if you think in that terms, the state is always the boundary in the sense of the processes. This is the logic being used, and unitarity it's slightly tricky here. Because unitarity, it's unitarity in time. It means two different things. A calculation, everything is unitary here in the sense that the probability is supposed to sum to 1, of course, and so on. But since there isn't a one parameter, a preferred one parameter time evolution, there's no unitarity in the sense that the Hilbert space doesn't have a representation of the time evolution, which is unitary. Just because time is always tricky in GR. That I just wanted to maybe help this with respect to your question. The third question, maybe I should let Francesca answer. What are the observables? The observables are geometries of the boundary, so area and volumes and angles of the tetraeder that discretize the geometry. So you actually make length and volume and area measurement at some point, and these are the things we talk about. Before I close, I've seen that Ofik has written in the Ofik there is time to address the question raised about the quantum as a universe. I think that's very important, and we need to understand it better. Can I say a word about just one, Deepak, but it says to everybody, but it starts by saying Ofik to come. Can I make one comment about that? Do you allow me, Francesca? Just because that's what
allow you, Carlo.
What Ofik, sorry, but just what the question Ofik asked at the very beginning, abusing his, that's the way you put it. I think the question is very good. It's very important, but it's very good to discuss it in the context of quantum. I would answer in the following way. I would answer by asking you, Ofik, when Marcus makes an experiment in his laboratory, he uses the quantum mechanics of the thing he's doing about it. Isn't Marcus quantum? What about the quantumness of Marcus himself? And of course, you have an answer to that, okay? Which is an answer that has to do with how to think about quantum mechanics. So I think the point about quantum gravity is that whatever answer you have in the non-relativistic case, the same answer can be translated in quantum gravity. There may be some dots to fields, but the question of the interpretation of quantum mechanics, why, if you use the standard Copenhagen, the apparatus is classical, but what about apparatus being quantum? It's not the question of quantum gravity. They're two different things. And somehow the message don't hope to solve the quantum mechanical mystery by looking at quantum gravity. You still have the same mystery. You may have additional things not clear, but those can be answered. Like where is where do I put the separation between myself and what I consider, what I treat as a quantum system? And those are the questions to which Francesca was giving answers. I don't know if this helps clarify this subtle issue about the connection between the quantum interpretation mystery and quantum gravity. I think the more we keep it separate, better it is.
Yeah, yes, this is sort of the answer that I also understood when I asked it. Yes. Yes. Okay. Deepak, you have anything to add?
No, I mean, like my point is not that I'm not saying that, we need to look for solutions to the measurement problem in quantum gravity or anything like that. What I'm saying is something much more conventional. It is in the context of many-body physics and thermalization. So one of the questions in many-body physics and the way we do quantum gravity, at least in loop quantum gravity and spin forms, it is many-body physics. So one of the questions there is that if you have an isolated system, and again, as Francesca said, there is no such thing really as a truly isolated system, which is, true, but let's take it as for the time being. And you ask that it starts out in the universe starts out in some kind of pure state, right? Then how is it the case, for instance, that at some later stage in time, I as an observer look around me and I find that the universe is in a mixed state, or some subsystem of the universe is in a mixed state, right? So how can the whole system itself be in a pure state, while at the same time, observers within that system can look at different parts of the system, right, and not see them as being in pure states?
Well, decoherence, yeah.
Well, decoherence is part of that picture. Quantum Darwinism is part of that, of the overall explanation. But so the answer lies in something called the entanglement thermalization hypothesis, and it's something that's studied in many-body physics. And it is not an attempt to solve the measurement problem by looking at quantum gravity. It's something very, very conventional. So. But whether or not this answers your question about quantumness or classicality, I don't know. I mean, I guess that's a topic for a longer discussion.
It seems to me that what you're hinting is more about systems that have quantum or statistical correlations rather than so how we study these differences and how different observers may have different answers. So I think this is something very nice. It goes in the direction of perspectivalism and relationality. So this is something I like a lot. And again, what is nice in loop quantum gravity is that having this lattice-like structure is very easy. I mean, one can try at least to connect with condensed matter systems. And I mean, Eugenio, for instance, is somebody who has been doing a lot in this direction. So yeah, I think this is something interesting.
Okay. Thank you everyone for your questions. Let's thank Francesca.
Thanks to all of you for joining today, and I look forward to see you in person maybe. It was wonderful to see all of you in Vienna recently. It was a wonderful event. So thank you again to Marius and to Czeslaw and Marcus and all the people that made it possible. It was nice to see you in person, and I hope we can continue.
Thank you, Francesca.
We will continue to see each other online and in other forms. And we have one more seminar, right, Ofek?
Yes. In a month, Andrea Di Biagio. There he is in Western.
Yeah.
hiding in the corner.
Send me an abstract, Andrea.
No worries, I will check it. For you. As long as he is with us, I will check it for you. Okay. Thank you so much. Thank you, everybody.
Thank you.